Alright, so I received my first email request for help on the Chapter 11 exercises, and specifically the question was with regards to part 2 of the first exercise. And so before we even look at the problem itself, the big challenge with these problems is there just becomes a lot. There's a lot to deal with. There's a lot to handle. Okay, and so bear with me. It may take me a little while to get things up and running, but just one strategy as you tackle these is, it's meant to kind of be a progression, right? So, it says start with our human cannonball problem, so our 2D trajectory code in which we solve for the optimal launch angle in vacuum, right? So, what's the optimal launch angle? Well, if I know what the launch position is and I know the initial launch velocity, I'm just going to look at a range of launch angles, and my optimal launch angle is going to be the angle that results in the largest distance traveled, right? So if I compute distance traveled as a function of angle, optimal angle would be the one that gives me the largest distance traveled. And so then the hope was in 1, right, we do a simple update, right, on that code in which we account for air resistance, okay? So we would update our acceleration. Then in 2, the idea is, okay, so now that this code's working, now we're asked to compute the optimal launch angle over this range of masses, right? So we're going to look at the effective mass. So the thought would be is if in part 1, right, I have this black box, right? Now I have this black box where for a given mass, it'll return the optimal launch angle. So now I want to build on that, and I want to look at a range of masses, right, which screams for loop. So I want to set up, say, a for loop that's going to loop over a range of masses. And for each mass, I want to perform this calculation to return the optimal launch angle. Okay, and so the hope was it would kind of take it in steps like that, because otherwise it becomes a lot. So let's take a look at the code that it received, see if we can get it running and working. I'm guessing it's more so their code they had for part 1, and then let's build it up. Let's go through the exercise together. And this is one of the unfortunate things with not having class together is being able to go through some of these exercises together. Okay, well, so the code has no input. So let me just go ahead and let's try and run it and see what happens. Okay, so I'm just going to run projectile model 2. It has no inputs, and just see if it actually works. And it doesn't. So we get an F0 error. The projectile returns a vector of length 6, but length of initial conditions is only 4. So we're calling it as if we have 4 variables, but 6 are being returned. Alright, so let's figure out where projectile is and go from there. Okay. All right. So code. So we have our initial positions, and so these are highlighted in Cheyenne. So remember, if you have variables that are highlighted in Cheyenne, that means that they're going to be shared between multiple functions. So if you have, say, a nested function, so we have our initial position, initial velocity. Looks like here's our range of angles we're going to consider. So one more tip too is, while I'm still kind of in the testing phase, I'm going to make this increment, this angle increment, a little larger. Once I get it working, then you can shrink it down as much as you want. But this way, if it doesn't work, I'm not waiting a little bit for the answer to come back and see it's not working. Compute the x and y component of the initial velocity. Okay, so these are going to be vectors. Okay, that's good. So you just compute them all at once. Initial time. Size a vector to keep track of x impact. Okay, so for each angle, we'll get the distance traveled. Looping over initial launch angles and solving for the distance traveled. Okay, so m we're creating as an empty vector because ultimately it'd be defined here. Okay, we're even sharing the index variable. Great. So I is 1 to length theta t naught. T impact is F0 projectile solve. Okay, so if I look at projectile solve, so we're basically, the goal of this is going to be we're going to loop over all of our angles. For each angle, we're going to compute the distance traveled. And then we're going to collect that in a vector, and then we'll look at that to find the max distance traveled. Okay, so let's take a look at this. So that's projectile solve. Projectile solve solves our ODE from T naught to T. Okay, T. All right, F0 is going to iterate on T until we get an M of 0. All right, so it's going to integrate from T naught to T. Okay, where F0 is going to iterate on T. We have initial conditions X naught, Y naught, Vx naught I, Vy naught I. That's right. Then M is going to be my matrix. Okay, order of my columns, looking at my initial conditions, is X, Y, Vx, Vy. So M, N comma 2, this would be my last row, second column, so that'd be my final Y position. So that looks right. So that looks right. This just needs to be value greater than 0, and this, how we'll determine if if this needs to be adjusted is if we get an error message that F0 failed because the sign was the same at my two endpoints, then we can take a look at that. All right, so that's projectile solve. That's dependent on projectile, and projectile is what was giving us issues. And I also need to keep track of all this stuff. So that function ends here. So this function is nested. And you have some text after it, which is fine. My preference would be to move this to the end of the function, right before the end statement, just because this becomes a little harder to keep track of then in terms of the break. All right, so I'm going to do that. Okay, and this is just me, right, and it becomes easier for me to keep track of what's in that top function. Okay, so let's look at projectile, because that's what was actually throwing the error. So if I look at projectile, okay, so we have initial conditions. We have 4 initial conditions: X naught, Y naught, Vx naught, and Vy naught. So we're looking at a specific I. So that's our loop index, so a specific value of the velocity vector. So W should definitely be of length 4. So then P is W12, V is W34. That's fine. That's a vector of length 2, vector of length 2. dP dt is V. dV dt is acceleration T, PV. Then we pack it up. Okay. So what I'm trying to look at is, remember the error message when we ran is that projectiles returning a vector of length 4. So if I look at acceleration, P is not used, but that's okay. GC, mass. So this is where I think we're running into problems. Okay. Because if I have mass defined as a vector, this is a vector of length 100. So then F drag. Okay, so this is going to be a vector of length 2. But then A drag is what? So F drag is a vector of length 2. Mass is a vector of length 100. So I'm not exactly And then the other thing that's not clear to me is how MATLAB's working internally is if it's treating W as being a column vector or a row vector. And so I suspect that might be where issues coming in. Okay, so that's not necessarily well. Let's talk about mass, but let me just do mass is equal to 75. Okay, let's just see if we can get the 75 kilogram case working. Okay, because again, my strategy is going to be to get this working and then figure out how to set up this for loop. Okay, so all I did is comment out your mass here, make that 75. Okay, so I'm going to save this. Okay, and I'm going to try and run again. Oh, still doesn't like me. What don't you like now? Line 31. So all I did is change that mass, the theta naught, I shrank the range. What is going on? Let's look at projectile solve. T naught to T. This looks fine to me. Arc. Alright, let's blow this up. Let's look over it again. So X naught, Y naught, V naught, theta naught. So all I did is shrink that up. Vx naught and Vy naught are going to be vectors. Okay, but they'll be the same size as theta naught since I'm using vector operations. T naught, X impact, it's just the same size as theta naught. That's fine. I equals 1 the length theta naught, that's fine. Okay, then we're going to solve projectile solve. Projectile solve is nested so that you can see M. So projectile solve is I'm solving from T naught to T, subject to initial conditions X naught, Y naught, Vx naught I, Vy naught I. That's fine. Then returning the Y position. So M's a matrix, but this would be last row, column 2. So then F0 I don't see an issue with that. Let's look and see if there's something wrong with projectile I didn't notice. Okay, so now this is projectile again. W is of length 4. XY, VX, VY. Yeah, so W has to be, so V has to be a column vector, right? Because that just tells you, right? We're doing a vertical catenation, and so I think the issue here was length space is going to create a row vector. So this mass is a vector of length 100, a row vector of length 100, where F drag is a column vector of length 2. And so I'm guessing you're going to end up with a drag acceleration matrix. Okay. But anyway, so let's look at acceleration. sine v drag divided by mass. So now, I'm not sure if this is it, because so a drag, so f drag is here, v is going to be a vector of length 2, a column vector. Should it make a difference? Because colon just means, all rows. Okay, that magically fixed it. Okay, cool. Okay, undefined variable function mass. Okay, well, we get a max distance, we get an optimal launch angle, then that's on line 49. Alright, let's have some fun now. Alright, so on line 49, it's complaining about not having mass. So let's see what that's all about. Oh, okay. Yeah, we got this. We got this. So figure 2, I'm going to comment out for now. Okay. Let's see. Do we want to get mass working with less than efficient code and then make it more efficient, or should we make it efficient first? I guess in the purpose of this video, let's get mass working with our less than efficient code. That way, if you want to turn me off, you can turn me off. All right. So theta opt. I'm going to comment this guy out. Well, I can leave that for now. Okay. So let's just increase my angles. You had increment of 1. Let's run it. Oh, let me run it again. Let me silence it. And so we have, hey, cool, distance traveled. That looks beautiful. Okay, and then you've got an optimal launch angle of 43 degrees. Cool. All right. So let me blow this up, and now let's think about the mass part of it. Okay, and we could do this in a number of ways. Okay, boy, it's just a matter of how best to do it. Okay, let's do a black box route 1. So I have this set up. Well, no. Oh. Okay. Let's. So it's just a matter of, there's plenty of different ways to do this, right? So one would be, is what I'd like to do is try and sorry, I told you this is me genuinely solve it. So I'm trying to think about how I want to best set it up. So strategy 1 that I'm debating with is I can make mass an input to this top function. Okay, pass that all the way to acceleration, and so we can figure out how best to get mass from here to acceleration. At which point then I could just add a top function in which all I need to do is loop over mass. Right. Option 2 would be I keep this as a function with no inputs, and then set up the loop in here. But I think I'm going to go towards that other approach. So what I'm going to do is, okay, so right now I'm trying to see get X impact. Okay, I'm going to disable the plots. Okay, because as long as we assume that works, I really don't care about the plots. Okay, and we'll keep max distance X would be max X impact. That's fine. So you're using the max functions. Okay, and so I'm going to suppress this here because you have it returning theta not X impact. Okay, so if I keep 75 as an input there, okay, and I'm going to assume that this works. Okay, And let's just make this theta and x, right? Where is it? I don't want all these. Why is it? Sorry, I'm just trying to get it set up so all it does is return theta and x. So some output is not suppressed somewhere. I'm printing a vector of velocities. I don't understand. So what this should be, oh, it's because you're returning the vector of thetas and x impact. So what I want is I just want to return theta opt, basically, all right? And if you want, we can get max x distance. Let's return the maximum distance traveled, all right? And let's get the optimal launch angle too, right? That could be fun. So I'm going to return max x dist. Now I'm going to return theta opt. So rather than return vectors, okay, what's going to happen now is I run this function, and it's going to return that maximum distance traveled, and it returns the optimal launch angle, right, 43. Cool. All right. So now what I'm going to do is I take this in pieces. I want to make mass an input. All right. So the idea is down here, I specify mass as 75. So what I want to be able to do then is make mass an input, or even better, okay? Before I think about making mass an input, you know, if I were to specify up here that the mass is equal to 75, how can I get that all the way down to my acceleration file where it's needed? And then once we get that working, then we can make mass an input. Then we can add a top function, which is just going to loop over mass and solve for all the cases. Okay, so I'm going to get mass. I'm going to define mass up here in my top function, and my goal is to get it all the way down here. Okay, so the challenge is that these two functions are in parallel with my top function. Okay, so one option is going to be is we could just include these two functions within our top function. All right. That might be the easiest. Now, I haven't checked over any other variables to see if that would cause conflicts anywhere else, but that would probably be the easiest approach. The other would be if we were to try and use an anonymous function, we would have to get, what we could do is we could pass the mass to projectile, and then projectile could pass the mass to acceleration, right? Either or. It's a matter of if you want to use an anonymous function or not. Okay. Let's see. So if I look at this, if I look at projectile, there aren't going to be any common variable names. So we could nest this without a problem. Okay. So now this would have knowledge of mass, and you could see there's no shared variables. Okay. Now the question is, do I want to do that with acceleration, or the other option would be I could just pass mass to acceleration, right? So option one would then be if I type mass here, it's Cheyenne because it can see it because it's nested in my top function, and then I could pass it. Or option two would be I also nest acceleration in my top function. Okay, and if I do that, I'm looking for Cheyenne. The only thing I get in Cheyenne is mass, which tells me then that, you know, mass is the only shared variable, so this would be just as safe. Okay, so let's go that route. Why not? Okay, so if I minimize this, okay, let's see if we get the same answer again when I run it. Okay, so if I run it, all right, I get the same answer, 288 and 43. Okay, great. Okay, so we're progressing. Okay, so now what I want to do is, if we just keep taking this in baby steps, is I want mass to be an input. Okay, so I'm going to call this 75. All right, works just fine. Okay, I don't know if you can hear it, but my computer fan is humming. Some of these problems could be a little more intense. All right, cool. So then it's a matter of let's add a top function. I'm going to add a new top function. Function. Let's do res is, and this is going to be projectile model 2. And then I'm going to have to rename this. Instead of being projectile model, we'll just call it projectile model 2. We'll just make it model. All right, so what I want to do now here is I'm going to create a mass vector. Okay, and let's just do mass. I'll do lint space. And if I look, we're looking at 0.04593. Let's see if it'll let me copy. Oop. I'm going to go up to 75. And for now, when I'm testing, let's just make this a vector of like length 5. Right? So mass is going to be go from here to here, and it's going to look at 5 equally spaced pieces. Once I get it working with 5, I can make it as large as I want. And then what I'm going to do is for each mass, I'm just going to call this. And so let's get some collection vectors. We can call this like a max x vector. Max x will be we'll do zeros, and we'll just do size of mass. Okay. Then let's get our optimal thetas. And that'll be zeros, size mass. Okay. Then it's going to set up a for loop for I is 1 to length mass. Okay. What I'm going to do each time is I'm just going to call this animal. Okay. So, and what I'll return is it's going to return the max dist for a given mass. So I'll have max x I, comma, theta opt I is equal to projectile model mass I. End. Okay, cool. And then just initially to see if it works, let's plot mass, comma, theta opt. Black line circles. And let's see what we have. Oop. So now I run this again. I actually have no outputs. Okay, we'll leave res on there. Undefined function or variable mass. Right here, capital. Let's see. Okay, let me close this. Let's run it again. Interact with charts. Great. Okay. Cool. Looks like it's working. Okay. Let's pump it up and have some fun. Okay. So pump it up and have some fun. So let's make our plot a little nicer. So we'll make this, we can make sure it's labeled as figure 1. We'll make sure we have a hold on in case we want to do multiple things. Then my X label will be mass, and that's going to be in kilograms. So let's do mass in kilograms. Y label will be optimal angle, and if I look at theta naught, that's going to be in degrees. So if I do a backslash theta, this should give me the Greek symbol in degrees. Cool. So now we're looking pretty. Okay. Now we had 5 points before. Let's do 20. I'm not going to go crazy yet. I don't know how long this thing will take to run. Bam. Cool, looking good. Cool. Okay. So in theory, that should fix up your code. But if you want to keep watching, I think I'm going to keep trying to play around and have a little more fun with this if you don't mind. Okay. Cool. All right. So what I'm going to do to try and speed this animal up a little bit is there's a couple of things we can do with trying to find the optimal angle. Okay, and so you use the max function, which is fine. So basically, you're going to create a vector of distances traveled. You're going to find the largest one, and then you're going to pull off the corresponding value of theta. Okay. Now, where this can become problematic is, okay, let me pop up these optimal angles, right? So what we should find is when we have a heavy mass, right, my optimal launch angle is going to be close to 45, right? Drag's not going to be that important, okay? But then as drag increases, my optimal launch angle is actually decreasing, right? Because drag always acts opposite to motion. So when I have, wind resistance, when I'm moving up, drag's pushing me, down. So the greater the effect of drag, my launch angle is going to be lower, so I'm not pushing down on me quite as much. And so, here my optimal launch angle, it's going to approach 45, but then it's decreasing, right? I have a smaller value, the smaller the mass. And so, what I should have done is in exercise 1, when we were looking at distance traveled versus launch angle, you essentially should go through a maximum, right? And so what we can do is if we start with a low angle, maybe it even needs to be something lower than 30, we can just keep increasing. Then as soon as we realize that our distance traveled is starting to decrease, we could just cut it and pull off the last value, right? Would be one cool trick we could do. Okay. So what I'm going to do here is, I don't know what that lower bound should be, to be perfectly honest, but let's at least try with this other technique to soup up your code, and then we could play around with those angles as well. And so what I'm going to do is what I want to do is I want to check to see if I've gone over that extremum. So again, if I start at a low angle, right, so you're starting at 30. So as you increase your launch angle, you should go through an extremum in terms of distance travel. So your maximum's at that optimal launch angle, and then it's going to decrease for angles larger than that. So can we just have if x impact of I is less than x impact of, now we want to make sure, so if by some chance that angle's too small, this could break. So we're going to want to do, if I is greater than 1, and so I want to make sure I'm beyond the first iteration, and I want to check that x impact I is less than x impact I minus 1. So the goal of this would be is if 30 is in fact a poor lower bound for some of these lighter angles, then it might be that already for I of 2, or I of, well, no. What I can't do is if I'm on my first iteration for I of 1, I can't, do this because this would be unbound. So you could either combine it or you could nest it. So you could do if, x is less than 1, then you could have a check if. So make sure I'm beyond my second iteration. If x impact of I is less than x impact of I minus 1. So we can say this means distance is decreasing. Then we want to, let's see, return exits a function. We want to break. So break would exit the for loop. Okay? And so then the max distance traveled would just be x impact of I minus 1 and theta opt would be theta not I minus 1. All right, so again, what I've done here, or how I've changed it, is, we're increasing the angle from 30 up to 60, okay, and we're calculating the distance traveled. So we should have seen in exercise 1 is, so the optimal launch angle is the angle that returns the largest distance traveled. So as my angle increases, the distance traveled is going to increase until it goes through a maximum at the optimal launch angle. Then beyond that, it's going to begin to decrease again. So what I'm doing here is after I calculate my distance traveled in a given iteration, I'm checking to see if the distance traveled I just calculated is less than the last iteration, which means I've gone over that extremum, which means the last angle that I just considered must be optimal. And so I'm going to pull off the maximum distance traveled and maximum angle as being I minus 1. Right, I would just be the I of that last iteration, because here I am breaking out of that for loop. I think, fingers crossed. And so if I keep your code the same, okay, let's just run it again and see what we have. Right, so it looks the same. All right, and now we can go crazy. So now we know that my upper bound, so we know our upper bound essentially is going to be 45, right? But if you want to make it a little bigger, we can make it 50. But what I'm going to do is I'm going to do linspace. Okay, and okay, let me try and clarify what I'm doing here too, right? So I know we can adjust this range. The upper bound doesn't need to be 60, because as I go up to 75, right, essentially what happens is we found the optimal launch angle in vacuum is 45 degrees. As mass increases, the effective drag is going to decrease. Right, until mass is large enough, then that drag term is essentially negligible, and so we'd expect that upper bound to be 45 degrees. What I want to do is, playing with the angles, is this is a little choppy, right? And it's a matter of you're looking at these discrete angles, and so let's see if we decrease those, if we can make this a little more precise and make this a little more curved. Okay, and then I'm also unsure if in the limit that I go to 0, you're stopping at 30 degrees because that's my lower bound. Can we play with that at all? Okay, so first I'm just going from 30 to 60. Okay, I'm going to do linspace, and actually it doesn't matter if we have a big upper bound, because I now have this check in my for loop that once I find the optimal, it's just going to stop. All right, so it doesn't really matter. Doobie doobie doo. Cool. All right, it's looking a little more curvish. Okay, so that's good. Okay, again, the upper bound expected to cop out at 45, but let's make it 50. Lower bound though, let's make the lower bound lower. Let's make it 15 and see if we get any smaller angles. In theory, if you really wanted a good answer, we would use some of MATLAB's optimizers, but this is a perfectly good solution. It's just a matter of CPU time, I suppose. Cool. So what did I set that lower bound to? I had the lower bound to 15, and it looks like, yeah, it jumps down to a value that is, well, we return all that, about 17.8. Cool. All right. So yeah, you could have as much fun as you want. That's 20 masses. Um, that took some time on my computer. So cranking it up to 50 masses, I don't know if how much longer that'll take. Again, my computer's already humming. But from there, you could go crazy. You could look at as many masses you want. You could change the precision of the angles if that's what you want to focus in on. It really is completely up to you. If you wanted to look at more angles over that smaller region, you could do that and stitch them together. If you really wanted to be crafty, too, if I look at this, range of angles, so what it looks like the trend seems to be is as the mass increases, the optimal launch angle increases. And so what I could do, if I wanted to be crafty, is I could, set this lower bound to be the mass I found from the last iteration. Hey, that's a good idea. We could do that. Let me see if this is taking a long time. Okay, so look at this. So now we have 50 masses, right? It's looking even more smooth, right? In theory, we could increase the precision of our angles. But the last comment I just made is I see as mass increases, the optimal launch angle is also increasing. Okay, so what if I'm starting at low masses, if I take that optimal launch angle, and that could be the lower bound, or the new lower bound in my search. Let's do that. So I'm going to create a theta min. Okay, and so when I use linspace here, okay, I'm going to start at theta min. Okay, and if I wanted the same result as before, I can make that, like 15. Okay, that's cool. But what I'm going to do here is let's do this. Let's do, if it's the first iteration, so if I, theta min for the first iteration, so I'll do theta min is equal to 15. Okay, cool. And then what I'll do is after I find theta opt I, okay, after this I'll assign the value for the next iteration. Theta min will be equal to theta opt I. Okay, and so what I'm doing is after I've computed theta opt I, I'm going to assign its value to theta min, so the next iteration, that's going to become my lower bound in my theta search. Okay, let's see if that speeds us up. Hey, look how much faster that is, and look how smooth that is, right? Honestly, right? That's so. If I go back to what I had before, let me comment this out. So if I go back to our old version of the code, waiting. I could use time it if I wanted to time it, but then it becomes even longer because MATLAB's going to evaluate it multiple times. So when this pops up, again, the trend we're going to look for is as the mass increases, my optimal launch angle increases. And so, hey, if I'm going from low mass to high, I can take the mass from my last, or the optimal launch angle from the last mass I just computed, and that could be the lower bound in my search of angles for the next mass, because I know the mass has to be, or the angle is going to be greater than that. Oh man, maybe I even, okay, so it works, right? It took a while. It's a little choppy, okay? But if I do this update, where I take the optimal theta from the last iteration to be the lower bound of the next search, it's going to be even faster, right? And it's smoother, right? Look at that. Cool. And I bet even once I have that, let's go crazy. Let's do 100 masses now. Okay. So I do 100 masses. I might even want to get rid of the circles now in terms of, it's incredibly fast. So there's 100 masses. That looks like a pretty nice smooth curve, right? And who would have thought, right? This is a Diffie Q I would never ever think about solving by hand. But if you take it in these gradual steps using MATLAB, I mean this is pretty wild. You've got a plot for optimal launch angle as a function of mass, right? And so as mass increases, this should go to 45. But if I have a golf ball, my optimal launch angle is much smaller. It's like 17 degrees, right? And I'm not a golfer. We'd have to ask Dr. Almquist. And I think there's some Magnus effect and things like that in golfing. But, you look at your golf club, a driver, it should have a flatter face, right? Because the optimal launch angle, if I'm going for distance, is smaller. Okay? As the pitch increases, so essentially as the initial launch angle increases, the distance traveled goes farther, but, the maximum height increases. So with that, if you stuck with me, I think I have completely beat your code to death. Main strategy, though, let's see, if I think through, main strategy was getting code working so that if I specified mass, it could return the optimal launch angle, so that then I just added a top function which looped over a range of masses. Then the couple of tricks we applied is from problem 1 here, okay? Rather than just looping over a range of angles, calculating the distance traveled for each angle, then using max to find the maximum. That works, right? And that's what we did in problem 1. It's fine. But from problem 1, you saw that, as the angle increases, so if you start with some small angle, go to a large, as the angle increases, the distance traveled increases until it goes through a maximum, and then it begins to decrease. And so I just added this little check to see if, hey, my distance traveled is decreasing relative to my last iteration, at which point, just stop, because I know the last iteration was my max. Don't keep computing, because I know the distance traveled is just going to keep decreasing. And so that was one trick to make it a little more efficient. The other trick was, once we got this working, we saw that as the mass increased, my optimal launch angle was increasing. And so then when it comes to a range of thetas to search over, that, as my mass is going up, I can just use the optimal angle for my last mass calculation as the lower bound in my search. And so that really helped me increase my precision. So here I am looking at 100 masses. I've got 100 angles. You could even make that more precise. One thing we should probably have it do is get this so it returns those as well. And you could even return those. Let's return max x and theta opt. And maybe I even want to return the mass vector, right? I could return all those, right, if I wanted to. But, again, I mean, the code now, just with those couple of efficiency improvements, I mean, this is wicked fast. And we're looking at a finer theta helps out is the precision of this plot, right? I don't have all these kinks. But, this is, at least to me personally, I think this is pretty awesome. Right? So now you've accounted for drag in a Diffie Q. So I could solve a trajectory problem maybe by hand, right? So in physics, you would have solved trajectory problems in vacuum. I had drag, no way, right? Now I had drag, and I want to look at optimal launch angle. So keep solving this for a bunch of different angles and find the optimal, right? Or in theory, you could maybe do some tricks from calculus and try and optimize said resulting trajectory. But then to look at a bunch of masses too, it just becomes crazy, right? But here we go, right? We can do it, right? And the resulting code is pretty darn efficient. Okay, so before I stop, so again, just to, here's my top function, which I added, which is new, which is just looping over masses and solving for each mass. Here's my trick of using the optimal theta from the last iteration in the next one, and then getting mass all the way down to your rate function, right? All I did was I nested it, and I did it one at a time, and just noticed that mass was the only thing that was then colored cyan. And And so, okay, that's the only shared variable. It should be pretty safe. Okay, but all right, I'll leave it at that. Good luck.